All right, so let's start our class. Today we are moving to another aspect of fluid mechanics, which is hydrodynamics. Last week we treated hydrostatics, that is fluid at rest. So this week we are going to consider fluid in motion, that is hydrodynamics. So hydrodynamics is the study of fluid in motion. The study of fluid in motion. We have defined what a fluid is. So let's look at some assumptions for an ideal fluid. The first assumption is an ideal fluid is considered non-viscous, meaning there is no internal friction. The second assumption is it is incompressible, which implies that the density of the fluid is constant. At any point as the fluid moves from one point to the other, the density remains constant. And then the third assumption is the motion of the fluid is steady. It's not turbulent. The motion of the fluid is not turbulent, is steady. So that will take us to types of fluid flow. There are two types of fluid flow. The first is laminar flow, or you can say streamline flow, or regular flow, or steady flow. So laminar fluid flow is defined as a type of flow in which the fluid particles move along a well-defined path or streamline, and all the streamlines are straight and parallel. Now, we have two figures here. The first figure by the left is a demonstration of how laminar flow is. The fluid particles move along a well-defined path, along a straight line, parallel to one another. There is no interaction between the streamline. That is a laminar flow. Now, the second type of flow is turbulent flow. A turbulent flow is defined as a type of flow in which the fluid particles move in a zigzag, irregular, and erratic manner. The second diagram there shows a turbulent flow. You see that the flow is turbulent. It's not like laminar flow that is steady or well-defined. Here it is irregular, it is zigzag, it is erratic. So these are two basic types of fluid flow at this level. Now, how do we know if the fluid flow is turbulent or is laminar? We use what is called Reynolds number. Reynolds number. The type of flow is determined by a non-dimensional number called Reynolds number. So the formula is given there, RE for Reynolds is equal to rho Vd, rho for density, V for velocity of the fluid, D for the diameter of the pipe through which the fluid is flowing, over no. No is the viscosity. So R is equal to rho Vd over no, where D is equal to 2R. Since D is diameter, and if we want to rewrite this expression in terms of radius, D is equal to 2R. So we replace D with 2R to have the second equation there, which is R equals 2R rho V over no. 2R rho V over no. Now, if you're watching and you have not subscribed, just kindly click that subscribe button. You don't need to do anything else. Just click the subscribe button so that the subsequent lecture, you don't need to wait for the link. You will just be prompted. So if the Reynolds number is less than 2,000, it means that such flow is a laminar flow. And if the Reynolds number is more than 4,000, the flow is turbulent flow. Again, if the Reynolds number is less than 2,000, the flow is called laminar flow. And if it is more than 4,000, the flow is turbulent flow. So now in between 2,000 and 4,000, we need additional information to ascertain if the flow is laminar or is turbulent. If the flow is laminar or turbulent. Now, we have talked about viscosity in our previous lecture of last week under hydrostatics, but we can't do away with it because we are talking about fluid flow. So one of the important factors in determining the state of flow of a fluid is the viscosity. And we define viscosity as resistance to flow. Now, higher viscosity increases the tendency of the flow to be laminar. Example of such fluid is honey. While lower viscosity increases the tendency of the flow to be turbulent. Example is water. So when the viscosity is high, there is tendency for the flow to be laminar, to be regular, to follow a well-defined path. But when the viscosity is very low or low, then it gives room for the fluid to flow erratically or in a zigzag manner. Now we look at flow rate. What is flow rate? Flow rate is the volume per second, also known as flux. Flow rate is volume per second, also known as flux. It is how much of a volume of a fluid crosses a given surface area in an amount of time. How much volume of a fluid passes through a particular point at a given time. So the symbol for flow rate is Q. And since it is volume per second, the formula for flow rate is Q equals V over T. V for volume, T for time. Now we can split our volume to area and distance. Volume is in meter cube, measured in meter cube, or unit is meter cube, area meter square, and then distance in meter. So meter square times meter will give us meter cube. So our volume can be rewritten as AD over T. AD over T. Now, in our kinematics, we know that D over T, which is distance over time, will give us speed. So if we replace D over T with speed, we'll have V. The symbol for speed is V, as well as the symbol for velocity is V. So our flow rate Q is equal to V over T. Look at the V, that is volume over T. The volume is a capital letter, while AV, the V there is a small letter indicating that is a velocity. So don't mix up the two equations, volume over time or area times speed. Area times speed. That is our flow rate. So let's look at an example of how to determine if a flow is laminar or is turbulent. Again, I repeat, if you are not subscribed, kindly click the subscribe button so that subsequent classes, you will just be prompted immediately we come online. You will not need to wait for Subdean to send the link. Immediately we come online, you'll be prompted and you join the class. So click the subscribe button. So there we have an example, two examples to deal with. Calculate Reynolds number if a fluid having viscosity of 0.4 Newton second per meter square and relative density of 900 kilogram per meter cube through a pipe of 20 millimeter with a velocity of 2.5 meter per second. So we are asked to find the Reynolds number. Remember that our Reynolds number, RE is equal to rho VD over no. Rho VD over no. And now we look at the parameters that are given. No, which is viscosity, is given to us as 0.4 Newton second per meter square. The density is given to us as 900 kilogram per meter cube. The speed of velocity is given to us as 2.5 meter per second. And the diameter is given to us as 20 millimeter. 20 millimeter. So we have to convert 20 millimeter to meter first before we can use it. 20 millimeter to meter is 20 times 10 raised to minus 3. 20 times 10 raised to minus 3. So if you substitute the parameters, you are going to have 900 for density times 2.5 for velocity times 20 times 10 raised to minus 3 for diameter over no. that is density, viscosity, which is 0.4. So if you simplify that, we get an answer of 112.5. 112.5. Now, the information we have with us to determine if a flow is laminar or turbulent is that if the Reynolds number is less than 2000, then it's a laminar flow. If it is more than 4000, it is a turbulent flow. So our answer here is just 112.5 is less than 2000, far less than 2000. So this would be a laminar flow. This would be a laminar flow. So second example, calculate the Reynolds number if a liquid of viscosity 0.5 Newton seconds per meter square and relative density of 500 kilogram per meter cube through a 10 millimeter pipe flows with a velocity of 3 meters per second. So we take down our parameters using our Reynolds formula, rho VD over no. Rho density is given as 500. Velocity is given as 3 meters per second. Diameter is given as 10 millimeter, which is 10 times 10 raised to minus 3 meters. And no, which is viscosity, is given as 0.5. So if we substitute all the values, that will give us 30. 30 again is far less than 2000, which implies that the flow is laminar, which implies that the flow is laminar. So we move on to continuity equation and flow rate. There you see two figures. There's a figure there with a funnel. A fluid is being poured through a funnel into a container. And then we also have the one with blue color. Now let's analyze the one with funnel. If we continue to pour that fluid through the funnel into that container, at a point you will notice that the fluid will rise in the funnel. And we will need to raise the funnel for the fluid in the funnel to flow freely into the container. If we do not raise the funnel up and continue to pour the fluid, you will notice that the fluid will rise to an extent that it may begin to pour out, overflow, and begin to spill, pour out. Unless we raise the funnel, that is when the fluid will begin to flow freely. Then we'll have to pause a bit for the fluid in the funnel to go down before we continue to pour. So just this preamble I've given to you shows that there is no continuity in the filling of that container by pouring fluid through that funnel. Look at the shape of that funnel. You see that the part where the fluid is being poured has a wider area than the part where the fluid is coming out to enter the container. Now, if we reverse that process, and then the part where the fluid is poured, where we have a larger area, is turned upside down, and the smaller area is where we pass the fluid, pour the fluid into the container. We will not have any pause in that case. We will not have a situation where we will need to wait for the fluid to go in before we continue or raise the funnel. We will not have such situation. So the figure with blue diagram gives us that kind of situation. So that is what continuity is all about. You are pouring a fluid, or fluid is flowing through a pipe, and then there is nothing restricting it. It's flowing continuously without stopping. Right. So for that to happen, there are some assumptions we need to consider based on our ideal fluid that we considered earlier today. We have about 3 or 4 assumptions for an ideal fluid. So out of the 4 assumptions for an ideal fluid, we'll consider 2 of them and apply to this equation of continuity and flow rate. So the first one here is, if the fluid is in streamline flow, that is, the fluid is in streamline flow, laminar flow, steady flow. And then the second assumption is the fluid is incompressible. The fluid is incompressible. So if we consider these 2 assumptions, we can say that the mass of fluid passing through different cross-sectional area are equal. If the fluid flow is laminar and is incompressible, then the mass of the fluid as it passes from point A to point B will be equal. The rate at which the mass of fluid enters will be the rate at which it goes out. So if we use that condition, we will be able to derive an expression for continuity equation. So here we have written the rate of mass entering is equal to the rate of mass leaving. The rate of mass of fluid entering is the rate of mass of fluid leaving. So equal time. The time is equal. The rate at which it's entering is the same rate at which it's leaving. So we have 2 points, point A and point B, or A1 and A2. So at A1 is entering, at A2 is leaving. So we write an expression for the mass rate at A1. The mass rate at A1. So the mass entering will be mass over T, that is mass rate. So, but remember that since we are talking about fluid flow, volume is also associated with it, and the fluid, we also consider the condition of incompressibility, which means that the density will also be constant all through. So if we convert our mass to density volume, remember that density is equal to mass over volume. Mass over volume, that is density, is equal to mass over volume. So our volume So the rate of mass entering there, by converting our mass to volume, density times volume, and substitute, that will give us rho A1, V1, change in time. Rho A1, V1, change in time. Sorry that the V1 there is showing as a capital V. It's supposed to be a small letter V. A small letter V, because our volume, mass is density times volume. So our volume is divided into area and let's say length of the pipe. Area and length of the pipe. The way we derive from our flow rate. From our flow rate, the way we converted our volume to AV. Let me take you back quickly to see what we did for some of you that came late to the class. So here we have flow rate. Q is equal to volume over time. So we converted our volume to area times distance. So distance over time became velocity or speed. Distance over time became our speed. So that is how we got AV. The capital V is for volume, while the small v is for speed of flow. So that is what we have adopted here. So we have our mass is equal to density times volume. Remember, we are looking at mass rate, which is equal to m over t. Mass rate is m over t. So mass will become volume, density, and t, where volume is AV. AV. So that gives us density, area, velocity, and time is equal to our mass. So we do that for the first part and repeat the same thing for the second part. So the rate of mass entering is density, area 1, speed 1, and the rate, that is time. Then the rate of mass leaving is the same. Density A2, V2, change in time. Now, because we considered a condition that the fluid flow is incompressible, it means that the density is constant. So if I equate from the first expression, the rate of here, we said the rate of mass entering is equal to the rate of mass leaving. So if I equate equation 1 and 2, since the flow is incompressible, the densities will cancel. The density will cancel. And then another condition that we considered is time. The time is the same. The time is the same. So the change in time in equation 1 and change in time in equation 2 will cancel out. So when that happens, we'll be left with A1 V1 is equal to A2 V2. A2 V2. So this is our equation of continuity. A1, A for area 1, V for the speed at which the fluid is entering, that is in area 1. Then at the other part, we have area 2, Then V2, which is the speed at which the fluid is leaving. So A1 V1 is equal to A2 V2. This equation is known as the principle of continuity. The principle of continuity. So let's move on to next slide. Now, we want to look at mass flow rate. I think it's part of what we have just considered. Mass over time is equal to density AV. So let's look at that example. There's an example there. If you have a fluid with a density of 1,000 kilogram per meters cube flowing through a pipe with a cross-sectional area of 0.01 meters square at a velocity of 2 meters per second, the mass flow rate will be, now the mass flow rate we know is rho AV. Rho for density given to us as 1,000, area given to us as 0.01 meters square, and then velocity given to us as 2 meters per second. So if we multiply them together, that will give us 20 kilogram per second. Mass flow rate will be 20 kilogram per second. So another example, the speed of blood in the aorta is 50 cm per second. And this vessel has a radius of 1.0 cm. If the capillaries have a total cross-sectional area of 3,000 cm square, what is the speed of the blood in them? What is the speed of blood in them? So the speed of blood in the aorta is 50 cm. We consider that as V1, and it has a radius which is linked to area 1. That is where it is flowing out, flowing in. If the capillary have a total cross-sectional area of 3,000 cm square, that is A2, what is the speed of the blood in them? That should be the V2. So we are asked to find V2. We are provided with V1, A2. We don't know A1, but we can calculate A1. And now we know that the aorta or the capillary has a cross-sectional area, a circular cross-sectional area. So we assume that the area of the aorta is a circle. So the area of the circle is pi r square. R, which is the radius, is given to us as 1 cm. Another thing we need to mention here is all the units are in the same metric. So they are all in CGS form. That is centimeter, gram, and second. So we don't need to convert. We can calculate using all the parameters without converting to meter. So pi r square, we substitute r as 1. So that would be 3.14 times 50. all over 3,000. So that gives us our V 0.052 cm per second. Cm per second. So this is application of continuity equation. This is an example of continuity equation. The previous one, example of flow rate. Now, Bernoulli's principle. Bernoulli is a French scientist who seek to know how pressure is related to the speed of flow of a fluid in a system. So he came up with his own principle. So according to him, the principle states that the total mechanical energy of a moving fluid comprising the gravitational potential energy of elevation, the energy associated with the fluid pressure, and the kinetic energy of the fluid motion remains constant. So what were his assumptions in deriving this principle? There are two of them. Here, he considered that the density or the fluid is incompressible, which means the density remains constant. And then the second assumption he considered was that the fluid, there is no viscosity, that is no viscous flow. The fluid is non-viscous. The fluid is non-viscous. So he considered two assumptions of an ideal fluid: incompressible or incompressibility, and then non-viscous fluid. Those were his two assumptions. So how did he come about his formula that we saw here? P1 plus half rho V squared. P1 there is pressure at area 1. Then density V1, that is the speed at which the fluid is flowing at the entering point. Then the height of elevation of the pipe. So we have this for the entering part and then the exit part. P2 for pressure as the fluid leaves. Then V2 for speed, the speed at which the fluid is leaving. And then the height of elevation of the fluid, the pipe from where the fluid is leaving. So if you look at this diagram that is shown there, well labeled, you see there that the fluid is entering at A1 and leaving at A2. The fluid is entering at A1 and leaving at A2. So the work done on the fluid as it enters from A1 and then leaves at A2 is given as dW is equal to F1 dx1 minus F2 dx2. Now, F, which is force, is equal to pressure times area. So we replace F1 and F2 accordingly with pressure 1, area 1, and pressure 2, area 2. If you recall, when we are deriving the continuity equation, we converted volume to AV. We converted volume to AV. Before we did that, we said volume is equal to area times distance. So here now we have P1, A1 dx. So A for area, dx for displacement of distance. So if we combine the area and the distance, that will give us volume. The distance is differential, so that will give us a differential volume. So that is why you have in the third expression there that dW is equal to P1 dV minus P2 dV. So that is for work done on the fluid. Now, we'll also consider the kinetic energy. Because we know that the work done on the fluid was due to conservation of gravitational force and change in kinetic energy of the fluid. So the change in kinetic energy of the fluid we consider as decay is equal to half m1 m2 v2 square minus half m1 v1 square, half m1 v1 square. From our relationship between density equals to mass over volume, we know that our mass is equal to density times volume. Density times volume. So we replace mass. We replace mass in that expression with rho dV. Rho dV. So when we do that, we have half rho dV in bracket, open and close, V2 square minus V1 square. That is the change in the kinetic energy. Now, the change in the potential energy, remember that potential energy is mgh or mgy. Y can stand there for distance or height. So m, again, we replace m with rho dV. Mass is related to density and volume. So we replace mass with density and volume. So when we do that, we are going to have rho dV G. That is the expression we have here. Let me take a marker. The expression we have here. This mass is, remember, density is equal to mass over volume. So mass becomes density times volume. And since we are talking of change, that is differential. So we have mass is equal to density dV. The density is constant. The density cannot change. It's only the volume that can change. So that is why the differential is coming on the volume. So now we have an expression for our potential energy, our kinetic energy, and our work done. Our work done is equal to the sum of the change in kinetic energy plus the change in potential energy. So if we substitute all the parameters as we derived it before, we'll see that dV is common here, here, here. So the dV will cancel out. So if dV cancels out, we'll have the expression here, which is P1 minus P2 is equal to half rho V2 square minus V1 square, bracket open and close, plus rho G Y2 minus Y1. Now, if we rearrange this expression, we'll have, that is considering what is happening in area 1 separately, and what is happening in area 2 separately. That is where the fluid is flowing in, that is the entry point, and where the fluid is flowing out, that is the exit point. If we separate the expression to consider that, we'll have P1 plus half rho V1 square plus rho GY1 is equal to P2 plus half rho V2 square plus rho GY2. So this equation is called Bernoulli's equation. This equation is called Bernoulli's equation. It's an equation that relates pressure of a fluid and the speed at a given height. So the Bernoulli's equation of the principle could also be stated as, for a streamline flow, the sum of the pressure, the kinetic energy per unit volume, and the potential energy per unit volume remains constant. The kinetic energy, the pressure, the kinetic energy per unit volume, and the potential energy per unit volume remains constant for a streamline flow. So that is another way to state Bernoulli's principle. So let's look at an example. A man observes that 0.24 meter cube of water, 0.24 meter cube of water flows out of a horizontal pipe in 1 minute. If the inner diameter of the pipe is 0.5 meters, calculate the speed of water in the pipe. The man observes 0.24 meter cube, that is meter cube, not meter subscript 3, it is meter to power 3. Meter cube of water flows out of a horizontal pipe in 1 minute. If the inner diameter of the pipe is 0.5 meters, calculate the speed of the water in the pipe. Now, in this kind of question, the first thing to do, if you look at it, we are given volume and time. So you can determine the flow rate. Remember that our flow rate, Q is equal to V over T. V over T, and is equal to AV, where V, capital V is volume, which is 0.24 meter cube. And then the time is given in minutes. We can convert the time to second. That is 60 seconds. And we are given diameter. So we can find the area using the diameter. Pi d square over 4 will give us our area. Then the speed, we are asked to find the speed. So if we substitute those values, 0.24 over 60 that will give us 6 over, okay, let's just go straight to. So you have 0.24 over 60. And that will give us Q. So when we have our value for Q, we divide our Q by A, and that will give us our velocity. So we have our answer there as 2 meters per second. 2 meters per second. You have to convert the minute to second. Convert the minute to second so that you can, the unit will be in meter per second. Another example, an ideal fluid flow at 4.0 meter per second in a horizontal circular pipe. If the pipe narrows to half of its original radius, A, what is the flow speed in narrow section, in the narrow section? B, if the fluid is water and the pressure at the narrow section is 1.8 times 10 raised to 5 Pascal, what is the pressure at the wide section? So to answer this, the first thing to do for A, we use continuity equation to solve A to find the speed. And then B, we'll use the Bernoulli equation to find the pressure. Now, when you want to solve, consider the statement that says horizontal circular pipe. Since the pipe is horizontal, it implies that in the Bernoulli equation, the change in the height will become 0. The change in the height will become 0 because the pipe is laid horizontal. So Y2 and Y1 are on the same level. Y2 and Y1 are on the same level. So Y2 minus Y1 gives you 0. So rho G H, rho G Y2 minus Y1 section becomes eliminated. So we are going to have only the pressure and the kinetic energy per unit volume section only on both sides. So from the question, V1 is 12 meters per second. R2 is half of R1. We are asked to find V 2. So we use the continuity equation method to find V2. So V2 is equal to A1, V1 over A2. A1 is pi R1 square, while A2 is pi R2 square. And we have a relationship between R2 and R1. R2 is R1 over 2. R1 over 2. So we use that expression. The pi cancels out, and then we write R2 in terms of R1. So that gives us V2 is equal to R1 square V1 over R1 over 2 square. So R1 cancels, then we'll be left with 1 over V1 over 1 over 4. So that gives us V4 V1. And V1 is V1 is 4. Sorry, not 12. V1 is 4. So 4 times 4 is 16. 4 times 4 is 16. Now, going to the second question, where we are asked to find the pressure. The pipe is laid horizontally, so the height factor will be the same. So that part becomes eliminated. So if that is eliminated, we have P1 plus half rho V1 square is equal to P2 plus half rho V2 square. We are asked to find the pressure P1. So P2 is known, which is 1.8 times 10 raised to 5 Pascal. So we substitute in the values. The density, since the fluid is water, the density will be density of water, which is 1,000. So if we substitute the values, 1.8 times 10 raised to 5 plus half times 1,000, and the difference between the second speed and the first speed, which is 16 meters per second and 4 meters per second. 16 square minus 4 square. If we simplify that, our pressure is 3.0 times 10 raised to 5 Pascal. 3.0 times 10 raised to 5 Pascal. So before we call it a day, let's look at one of the applications of Bernoulli's equation. Now, Bernoulli's equation is applied to a Venturi tube. Venturi tube or Venturi meter is an instrument for measuring with accuracy the flow rate of fluid in pipes. Now, just like the previous example that we just saw, Venturi tube is always laid horizontally. And since it is laid horizontally, it implies that the third parameter in the Bernoulli's equation will be eliminated. That is, the parameter containing the height will be eliminated. So let's look at it. The pressure P1 is greater than if you look at that diagram, you see that the pressure in P at point 1 is greater than the pressure at point 2. Now, according to Bernoulli's relationship between pressure and speed, it implies that when pressure increases, because they are inversely proportional, when pressure increases, the speed will decrease. So at point 1, the pressure is greater than the pressure at point 2, which implies that the speed at point 1 will be less than the speed at point 2. So we have the expression P1 plus half rho V1 square is equal to V2 plus half rho V2 square. Now, let's assume that you are not given the speed of the speed V1 or V2, either of them, one of them is not known. We can, with the help of continuity equation, solve for the speed in okay, so okay, our time is up, but I want to round up with this. Now, like I was saying, that we can determine the speed, either of the speed, V1 or V2, using the continuity equation combined with the modified Bernoulli's equation for Venturi tube. So if we replace, look at the expression there, V1 is equal to A2 over A1 times V2. So if we substitute that for V1 in the Bernoulli's equation and simplify, we are going to have what you have there. V is equal to A1 square root of 2 So don't forget to subscribe. Very, very important. Very, very important. Don't forget to subscribe. Ensure that you click that subscribe button so that subsequent classes will not need to be troubling ourselves generating link. Once we come online, you get the prompt and then you connect. So we'll meet again on Friday to continue from where we stopped today.